Every stone taken here can flip who wins. Player 1 scoops up a batch of stones from the front. Their score is the sum. Player 2 takes another batch from the new front, and it keeps going like that. They keep alternating turns until only one stone is left, and the final gap between their scores decides the winner. Alice and Bob take turns picking up stones from a row, with Alice going first. On each turn, as long as there is more than one stone left, a player must grab at least 2 stones from the left end of the row, add up their values, and score that sum. That combined value then becomes a single new stone placed back at the front of the row, and the game continues from there. This is LeetCode 1872, Stone Game 8. I'm Kai. Alice and Bob both play perfectly, and the whole video comes down to tracking one running number. You're given a row of stones with values, and Alice moves first. On every turn, a player takes some number of stones greater than 1 from the front, adds their sum to their own score, and drops that same sum back as one new stone at the front. The game ends when only one stone remains. Alice wants the final gap between scores as big as possible. Bob wants it as small as possible. You just return that gap. Take the stones -1, 2, -3, 4, -5. Alice removes the first 4, scoring -1 plus 2 plus -3 plus 4, which is 2. That 2 becomes a new stone, so the row is now 2 and -5. Bob has no choice left but to take both, scoring 2 plus -5, which is -3. One stone remains, and the final difference is 2 minus -3, 5. The row can hold up to 100,000 stones, so anything checking every possible split is out of the question. We need something close to 1 pass. Values can swing anywhere from -10,000 to +10,000, which means you can't just assume bigger piles are always better. Negative stones make greedy grabbing dangerous. Forget tracking exactly which stones Alice or Bob grabbed, like keeping a running tab instead of logging every single order. All that matters is the current score gap. Alice's total minus Bob's, assuming both players play their best from wherever the game currently stands. At turn 1, you could stop at stone 2 or stone 3 or any point after. Each choice spawns a whole new game underneath it. By stone 100, you're evaluating more branches than it makes sense to even count. This is big O of 2 to the n, unusable past, a toy example. The only thing that matters right now is how many stones are left and whose turn is it. That's just one number, the starting index. So instead of a tree, we build one array, one entry per index. Still big O of n squared though, because computing each entry means summing a prefix from scratch. Pre-compute a running total as you walk the array once. Now the sum of the first x stones is just one subtraction away. That turns every linear time sum inside the dynamic programming into a constant time lookup. The dynamic programming itself is now the only cost left, and it can be flattened too. The tempting move here is to loop over every possible split x inside a recursion, since the problem statement makes x sound like a free choice. But the removed chunk is always a prefix. So after any move, what's left is just a shorter suffix of the same array with one merged stone in front. The sub-problem never changes shape, only where it starts. That means you don't need to branch on x at all, walk backward from the last stone, and at each index your best score is either take everything up to here minus what's already the best from further right, or let that running best stand. Carry it forward as one variable while you scan. No recursion, no nested loop, just one pass, right to left. Python's accumulate from iter2s does exactly the running total walk we just described in one line. The last entry of that prefix array is also the only option at the very last cut point, so that's where the running best starts. This loop is the whole backward pass. At each index, the current player either stops there, scoring prefix at I minus, whatever the opponent's best turns into next, or just lets the existing best stand. Whichever is bigger wins. Here's the whole function put together. We build the prefix sums with accumulate, start best at the very last prefix value, since that's the forced final move, then walk backward from the second to last index down to 1, updating best as either stopping here or letting the existing best stand. Whatever's left in best once the loop ends is the answer. This runs in linear time, one pass to build the prefix sums and one pass backward for the scan. with linear extra space for that prefix array. Talk is cheap, let's actually run this. I fed it all three of the problem's real examples, no cherry picking. Let's actually time both. Brute force took 298.34 milliseconds. The optimal version took 432.9 seconds. That's a real 6912x from actually running both just now, not a complexity estimate. Quick one for you. Why do we build the answer array from right to left instead of left to right? Pause and take a guess. Think about what each index actually needs before it can be solved. Each spot depends on the result just ahead of it, so you have to solve the later moves first. Right to left is the only order that works. Second question. Why do we compare skipping this move against taking it, instead of always taking the current prefix? Guess before I answer. Consider what happens if the current prefix sum is actually bad for you. If cutting here would leave a worse score, the max lets you skip it and inherit the next player's better outcome instead. Drop that comparison and the algorithm forces bad moves. We solved Stone Game 8 by realizing every move is really a prefix sum choice, not a raw stone pick. Scanning right to left and carrying the best running value lets one pass replace the brute force tree entirely. That brings it down to own time and own space.